Hello, class. This is Lab 9. This is your lecture portion for the lab. I just wanted to get you acquainted into what this topic will be about. So there are a few items we will discuss. You are welcome to use your lab as a portion of it. So there are two types of age dating. First, I'll do relative age dates, and then we'll discuss numerical afterwards. Relative age dating, these are some examples as to what will possibly be in your final. So the premise of this is to use field relations to understand which portions come first and which portions come last. So our first one will be superposition. Your superposition is to show you what is youngest and oldest. So you're going to use the example that the oldest will be at the bottom and youngest at top. Okay, that one's a pretty easy one. So if you can just imagine yourself pulling some sand off of the ground, and as you are taking the sand out off of the ground and you release, the sand that leaves your hand and touches the ground first will be the oldest. Sand that leaves your hand last will be the youngest. Okay, your is your second one will be original horizontality. So with original horizontality, what you are seeing here is that everything is nearly deposited horizontal. So it will change with however the earth moves, but as it's deposited, it will just be flat. So you'll see different layers such as this, where each layer is almost like a bed. It just continuously carries on. And that's your original horizontality. Your next one is lateral continuity. This is actually a really good picture to show here. Lateral continuity means that your landform is continuing, but there might be areas such as this that have been eroded away. So if there was no erosion here, you would continuously see this black come all the way through, and then you'd see this earth and all these others beneath. Okay. Your next one is principles of inclusion. Now, with the principles of inclusion, this is a really good example. You'll see that there's this one particular area or inclusion that looks very different from the surrounding area. Inclusions are that we have a way to kind of represent them. We can think of a chocolate chip cookie. If you go to the store, you buy the chocolate chips. Those are your oldest, but if you're making chocolate chip cookies, the dough will be the youngest. So your chips or your inclusions will always be older, and your cookie dough or the mass around it will always be younger. Okay. Your next portion of this will be principles of cross-cutting. Now, this one is pretty easy in my mind. This is like good cartoons that kind of represent it. It's an item that actually cuts through something. So in order for your cross-cutting relations to happen, it has to have something there first. So if you're trying relative age dating diagrams, you should already know that your first one in no way can be the cross-cutting one. I'll do another visual example. That way you can actually kind of see right here. We have the earth surrounding layers. It had to be there in order for this dike to come through. A dike is what we would call a mass of earth moving through another portion. Our next one are unconformities. So here are three good unconformity diagrams. In your handout or in your actual lab manual, you have something that looks like this. This is a good diagram to kind of look at, but it might be a little bit hard if you don't have the visual representation of it. So I will show you how it looks like this way. So your disconformity, what you have is you have like a sandstone area, and you have a change in lithology. So you have two different types of ground. An angular one, you have it's still doing the movement, so it has the tilt to it, and it's still very different from the above layer. And the nonconformity, you have an igneous layer or an intrusion, and it is changing the geology of the contact here. Another good example would be, this is a good example. You have here, this is an unconformity. What's going on here is you have a disconformity. You have an area up here that could potentially be like shale, and then you have down here, you have an area that's different, which could potentially be sandstone. Another unconformity would be like this, angular unconformities, where you have items tilted, and it's very different from the surround. For the picture resolution, it might not be able to show as clearly. Here's another angular unconformity, and yeah, so if there's any confusions that you have with this, it might be a good idea to check online. The visual representations will really kind of help you understand a little bit more. If you have any questions on this, feel free to email me. I have no problems with that. I will actually attach a couple pictures on our course documents. That way you get an idea as to what you are looking at. So that is it for the relative age dating. We also have absolute age dating, or numerical age dating, and what that deals with are different methods in order for you to find out an actual numerical date. So there are things such as half-lives. I'm sure that you guys have heard of them, carbon dating, radioactive decay, those type of things. And what the premise is that you're trying to see how much of the original is leaving the body of what you're trying to calculate, and what those differences are to turn into ages. In the lab, I don't think that it's the same as yours, but we have a table similar to this. It gives us an idea as to ages, as to when each item will decay. So just remember, if you're actually able to get a numerical value, you're going to be numerical age dating. If you have to look at a picture, you're going to be relative dating, okay? So just be aware of those. I'll put up an example in the course documents for numerical age dating as well. And your next video will be for part 1 on how to do your time scale. So stay tuned for that. Thank you.